Okay, now we're gonna talk about, I'm recording by the way. So now we're gonna talk about what the SR flip-flop, okay? So an SR flip-flop, we already defined the SR as the following. Here is the box. Here is the sign, whether that I'm positive or negative edge of the clock. Do you guys agree? And we have here a color which is representing the S and color representing the R. And then we have here the Q complement. And we have here the clock, and I already told you what is the clock and how it looked like and what exactly we're expecting from the clock, which is called edges. Do you guys agree, or do you remember?
Was that the falling edge with the triangle? That's
What?
the falling edge.
Huh? You know, if you want, you can look at the recorded lectures, but you know, I'm not gonna repeat it because we need to move forward. So if you look here, here is the clock, right? If I go like this, that means from the low to the high, this is the positive edge of clock, or they call it what? Rising edge. Okay. And then, there is another one, which is basically this one. I'm going from high to low. So this one, that's called what? Negative edge of the clock, or the falling edge. Sounds good? Normally, when we actually use it in the, if we would like to write it in the truth table, how can we do it? We just do it like that. Look, that's called positive. That's called falling. Okay. Now, the symbol of this flip-flop has the triangle, as you can see here, right? There is no circle inside the triangle. So this is actually what? Reporting in the positive edge of the clock. Sounds good? So if I do the same architecture and just like, do like this, SR Q complement. So I'm talking about what? I'm talking about this flip-flop is SR flip-flop, but actually reporting in the negative edge of the clock. So this is actually negative edge SR flip-flop. Any questions so far regarding this? Hello?
No.
Should we move forward?
Yeah.
Now, now we need to work on the 3 different things I already promised you in the beginning of the sequential. So to define the characteristics of any flip-flop, you have to study 3 things. One is called truth table. One is called characteristic / state table. So some of the books are calling it characteristic, some of them call it state table. Okay, and the third is called what? Excitation table. So far so good. This is basically what we're going to work with from now until we finish the course. Characteristic, excitation, truth table. Now, if you guys remember, what was the difference between SR flip-flop versus SR latch? What was the difference? We add the clock. Do you agree? Because we said the latch, it's cool, it's super cool, but we found based on SR latch, Nando, NOR, that there is one state will not be used. Do you agree?
Mm-hmm.
And in the top of that, we said, there is no time. So if I just like hook S and R with 0, 0 or 1, 1, and depend on if it's NAND or NOR based, then I will be in a memory state. But I cannot do anything until manually change by my hand the SR, then I will let the data out and change, right? So we are adding aspect now of adding time to the circuit by including an extra input called clock. Do you guys agree? And how can we do this in the normal circuit? If we have here, for instance, NOR gate like this, and I have here NOR gate, and I have here the color of the For instance, like this and like that. This is what? This is the latch, right? And here is Q, and here is the Q complement. That makes sense? And what is this? That used to be our S and R. Do you guys agree? So here I'm gonna call it S star, and here I'm gonna call it R star. Why? Because those will be going into the clock by adding extra gate, which can be NAND, or it can be NOR, whatever you want. NAND or NOR, it can do the job. Okay, NAND or NOR, it will do the job. So let's imagine everything, it will be NAND based. So, I have here NAND, and I have here NAND, and I have here S, and I have here R. And who is this? That's gonna be our what? Clock. By this way, I turned my SR latch to what? To be flip-flop. Any question? Are you guys following what I'm saying?
Mm-hmm.
Okay. So maybe let's just stick to make this also NAND, so you guys will not be confused. Here's NAND also. But there is no problem to make it NAND or NOR. Who cares? Still, those are semiconductors. Anyway, if you look to this, you can actually come into a conclusion, and this conclusion will be our what? Truth table. So what is the truth table will look like? It will look like there is an S, and there is a clock, and there is an R, and I'm actually producing Q and Q complement, as we learned before about the truth table. Do you guys agree? So our truth table will be like this. There is a R, and there is Q, and there is maybe we can make R and S, and there is clock. Three things, right? So excuse me. If the NAND gate, I don't remember NAND gate. Do you remember NAND gate? NAND gate, it was N flipped, right? So if I put it like here and say that, I have X and Y, 0, 0, and then, 0, 1, 1, 0, and 1, 1. And in the NAND is an N flipped. Do you guys agree? So in that case, everything will be 1 and 0, right? So gonna be 1, 1, 1, 0. So what we learn out of this from your point of view, we learn out of this that, if the X is 1, that means one of the inputs are 1, then, it depends on what is the Y, Z will be flipped. Do you guys agree?
Yes.
So I can write it in a statement saying that, if one of input equal 1, then output will be second input complement, right? So if I say this is a positive edge, so pretty much positive edge is going from the low to the high. So this table will end up being what? Covering 4 states, not 8 states. Do you guys agree? Because anything else, it will not be reporting output.
Does
right?
it act kind of like an enable?
Exactly, is an enable, yes.
Okay.
So here we're going to be like 1, 2, 3, 4. Here is the Q and Q complement. Who will be the responsible on this? Look, here is this 1, right? Here is this 1, 1. So now, I'm looking to S and R, right? So if it's 0, 0, 0, 1, 1, 0, and 1, 1, right? Let's look at it. So now, I have here, this is 1, and I have here R is 0, and I have S is 0. Do you guys agree? So in that case, what is S star and R star will be? Somebody can tell me. They're going to be 1 and 1. Right?
Correct.
Okay. Then we will back. If it's 1 and 1, then end of the day, the second input will be the one responsible on what will happen after that, right?
Yes.
So pretty much, if the Q here So they're gonna be Q bar. If the Q bar go in here, it's gonna be Q bar, Q bar, it's gonna be Q, right?
So storing.
You know what I'm saying, right? Look, let's say that I'm not gonna take it with 0 and 1. I'm gonna take it with symbol, right? So if I take it with symbol, now this wire is holding Q bar. Do you agree?
Mm-hmm.
So put it here, Q bar. But I have 1 here. So this Q bar will be what? It will be output as a Q bar, Q bar. All right? So that's gonna be Q. And then if you reverse this Q here, they're gonna be Q. And actually this ones are gonna be what? It's gonna be Q bar complement. So they're gonna be storing. So this is a specific area I'm gonna store, right? Then as we learn with 0 and 1 and 1 and 0, it will be flipping, like set and reset, right? So for instance, now, my reset is 0. My reset is 0. And, I have 1 here. So pretty much I'm still 1. But, my set is 1. So pretty much they're going to be 0, right? So if there is 1 here, so pretty much, I'm waiting for the 0 here. If any 0 here, no matter what is the input here, the output will be 1. And that 1 will go here, 1 and 1, and the output will be 0. So it's going to be here 1 and 0, and here is 0, 1, and here it's going to be unused. So everybody's following me or not? If there is any question stopping me, stop. There is no problem. I'm very slow. Go ahead. Is it clear to everybody what I did?
Yeah.
Yes.
Any question? There is no question. Now we're gonna move to the next step. What is the next step? Next step is the characteristic table. Characteristic table or state table. So characteristic or state has a very nice rule, which is basically the combination between of the current state and the inputs, which will produce to me the next state. The current state with the inputs producing what? Next state. So how can we write this in the truth table? It's gonna be current state. Some people write a QN. Then inputs producing what? Next state. If the current is called QN, the next state will be what? QN plus 1. Some books will just do it Q, and then they will just Q star. So Q star, it will be the Q plus 1. Okay. How I'm actually prefer to do it is basically N and N plus 1. So this is the characteristic table. So again, let's define it together. So I'm in a state, right? The input with that state will help me to define what is the next Q. Because if you notice, we are every single clock, we are producing new output. Do you agree?
Yeah.
I would like to be sure that everybody of the 24 people sitting here in this course now know what I'm saying. So everybody following me, or there is something in the middle is not clear?
Could you repeat it one more time, please?
Sure. So, this is a flip-flop. That means it's associated with what? Time. Do you agree? So that means every single time something will happen. Do you agree?
Yeah.
So, since, the clock is periodic, that means, it's turn of pulse, right? On, off, on, off, on, off. So on, off, repeated many times. So end of the day, every clock something will happen. So the Q will bring Q plus 1, the Q plus 1 bring Q plus 2, Q plus 2 bring Q plus 3, and so on. That's why I call it QN plus 1. Right? So characteristic table will be taking S and R as an input with the current state and defining the next state. What the next state will be? Okay, which is the new QN. Do you remember when I put the Q here with 1 and 1, and then I 1 and 0, and then I flipped it, and then we found it again 1 and 0, then we said storing? That's basically what I did, the current state, and then I checked the next state and found it the same thing. That's why I said storing. That makes sense?
Yeah, I got it. Thank you.
For the rest of you guys, is it clear or not clear? If it's not clear, there is no shame, we are learning here. Now, I'm moving towards filling the table from the truth table. I'm filling what? The table from the truth table. Let's see how we're gonna do this. First of all, from whatever we learned from the numerical chapter, truth table has a three states, three inputs. So how many states this table will be covering?
8.
8. So let's do it. 1, 2, 3. Oh, shit, I'm sorry. 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. So far, so good. Now we need to check the QN plus 1 based on the knowledge I have in this table. Sounds good? Okay. So SR is 0, 0. When we said SR is 0, 0, what will happen here? I'm going to be storing, right? Jonathan?
Yep.
What does it mean storing? It means that current will be the present. There will be, sorry, the future, right? The present will be the future, right?
Right.
So my present here is what? 0. So my future is what? 0. I'm storing. That makes sense?
Yeah.
Now, 0, 1, it doesn't have any relation with the current state, right? Make sense? So 0, 1 is gonna be 1. 1, 0, 1, 0, Q is 0. 1, 1, unused. Again, 0, 0, the current state is 1, next state 1. 0, 1, 1, 1, 0, 0, 1, 1, unused. So what I did now, I filled in front of you the characteristic or the state table. It depends on which source or reference you are using. Any questions so far?
Professor, I'm sorry, I'm not seeing how the row right above unused, how the Q turns back to 0. I'm a little confused on that.
In which way? Which one? Which state?
So
Should
it
I
says
do that from the scratch?
the second to last state. So you
This
see
one?
yes, that one exactly.
Okay. 0, 1 is 1. Look here. 0, 1, Q is 1.
Okay.
1,
got it.
0, Q is 0.
Awesome.
0, 1, Q is 1. 1, 0, Q is 0. 1, 1, 1, 1 here. Whatever happens in the world is unused. It's gonna be here unused.
All right. Cool. Thank you.
The Q complement doesn't have any bearing on this characteristics then?
No Q complement here, right? Because I'm an SR flip flop. In the JK flip flop, you'll see it.
Okay.
Okay. Anyway, so far makes sense to everybody.
Sorry, I had a question about the 0, 0. I thought the 0, 0 was supposed to be stored.
0, 0 stored. That means the present will be the next. So here, look, 0, 0 store, right? What is the current 1? The next
Gotcha.
is 1.
Right.
0, 0 store, the current 0. So the next will be 0.
Okay. Thank you.
$5. Okay. Anyway, we filled our characteristic table. You can imagine anything you want, right? I can ask you to make an implementation of it, right? It's a normal problem, right? Somebody will tell me, what do you mean by a normal problem? I can tell you, implement it for me. Can you implement it for me now? You're gonna make K-map, right? Do you agree?
What would the unused be in a K-map? Would that?
That's a very good question. Maybe we can make it Z.
Okay.
You remember Z, right?
Yeah.
Or you can make it X, right? That does make any sense to you guys?
Yeah.
Yep.
So
Also, this
unused will be
table-
X.
Yeah.
So it could be 1 or 0. Okay.
Yeah, this table is running with clock is positive. Make sense? Because it's like, Kerry was saying that, it's the enable, right? This table will be useless if, I'm in negative edge, or it will be in whatever low or high, whatever, in a positive edge, this will happen. Or in the negative, if the flip-flop is designed to be negative edge, it will work with negative edge. That makes sense?
So will the element stop storing once it hits negative edge?
The opinion is not working.
Okay.
It will not stop, but it will be like in paused, right? I'm doing nothing,
Okay.
right? Any other question before we move to the next? So I'm not gonna make the implementation. It's really straightforward for you, right?
Quick question. So the SR, we still have to physically change it from 1 and 0, right? There's
course.
nothing that's changing
Yeah,
it.
any flip-flop, you have to change the input. That's the whole idea that I want to tell you, Sarah, that flip-flops is not just by self element. You have to put it in a big design, right? So in the design, when I will go through maybe next week or something in the design, you will see that, oh, now numbers are changing. Like, when I build a counter, input are changing, right? When I build a register, input are changing, right? But it's changing within the table, right?
Mm-hmm.
Okay, so is it clear to everybody? Shall we move to the next?
Yeah.
Yep.
So now we're gonna go into our lovely part, which is the next. What is the next? The excitation table. So in the excitation table, with the present state and the next state, I will guess what is my input. Because if you remember, the definition of the sequential, it's a combinational circuit with a delay, which is a loop back. Do you agree with that? Do you remember when I made it in front of you? Here's the circuit, here's an input, here's an output. You will put here like some delay, and then you will move like this, and then you will start moving like this. And that delay we call it flip-flop. You guys agree? So in that case, we need some table to tell me what will be the input when I will know the present and the next state. That's called excitation table. So now we're gonna get the excitation table. I'm getting what? Excitation table. So how does excitation table look like? So the excitation table, it has the Qn and Qn plus 1. So that means the present and the next state. And I'm getting the S and R as my output for this case. This table is covering how many states? 4 states. So it's gonna be 1, 2, 3, 4, right? So 0, 1, 0, 1, 0, 0, 1, 1. So far, so good?
Yes.
Guess who will help us to get the excitation table filled? The characteristic table. Huh? Who will help us to get the excitation table filled? Characteristic table. Okay? Let's see how this will happen. So I have Qn is equal 0 and Qn plus 1 equals 0. So I'm gonna go in my table and I will use some color, and I see Qn is equal 0, Qn plus 1 equals 0. Is there any other location that both of them equal 0 also? Yes, this one. Is there any other location in the table? Can you guys see any other 0 there?
No.
Super. So in that case, I know that in this particular state, SR will be 0, 0. Right? In this particular state, SR is 1, 0. So pretty much I can merge them to be what? X, 0. Do you guys agree?
Yes.
Yes, yay. We finished. Let's move to the next state. So what is the next state? Let's do it. The next state is what? 0, 1. So I'm gonna go with a different color here. So where is 0, 1? Excuse me. 0, 1. Is there any 0, 1? Can you see any 0, 1?
Other ones.
Yep, so gonna be 0, 1. That's it. So I'm gonna just write here and write here what? 0, 1. Let's move to the 1, 0. So I'm gonna get here the different color, which is gonna be 1, 0. With our 1, 0. 1, 0. Is there any other 1, 0 here? I don't see any 1, 0. Can you see any 1, 0?
No.
There's nothing. So it's gonna be 1, 0, right? So I'm gonna just write here 1. Then I'm gonna go into the last one, which is 1, 1. We have ton of 1, 1, right? 1, 1, 1, 1. So in that case, it's gonna be 0, and here is 0, 1, it's gonna be 0x. So congratulations, we finished the 3 tables describing SR flip-flop. If anybody asks you to do implementation for them, you're gonna follow the same thing that we did with KMap, and you will build it up. That makes sense?
Do all sequential circuits have all 3 of these tables?
Yes. So JK flip-flop has 3 tables. D flip-flop, it's actually it's a portion from JK flip-flop, and the T flip-flop is a portion from the JK flip-flop.
Okay.
Because there is a historical story about it. The history coming out of it, telling you that people didn't like that SR is handicapped and is not using all the states. So the designer and the mathematician came into a conclusion: we have to find a solution to use the unused state, and they built the JK flip-flop. Sounds good?
Sounds good.
Okay. So we learn now the SR flip-flop, and we close everything about SR flip-flop. And the only thing that you need to do is to make a real implementation using the KMap and fill the documents, and we'll be done. That makes sense? Like characteristic table, if you make the implementation, it will be just like whatever we already have done in above. Now we're gonna move to the next, which is a solution for covering the unused state, which is called JK flip-flop. So we're gonna go now into something that's called JK flip-flop. Before we go to the JK flip-flop, I used to teach this course in a way, and I'm trying to use a different way to make it more easy. I'm just trying to every time change a little bit. There is something is called the finite state machine. But maybe after the JK, I will try to introduce it to you. Then we'll return it back to D and T. So then it will be both of them melt together. That's my new way. And it should be easy. So believe me, it's gonna make it much better for you. But anyway, let's go to the JK flip-flop. Symbol-wise, when I build it in a big circuit, so the JK flip-flop like this. I have here J, I have here K, and I have here also Q and Q complement. And either that I'm gonna be positive edge of the clock, or I'm gonna be what? A negative edge of the clock, and I have here J, and here I have K, and I have here Q, and I have here Q complement. It looked like SR, right? I just changed this on R to be J and K, right? Do you guys agree?
Yes.
But
Yeah.
now,
How can you tell the difference? Is it like a chip? Is it a different chip number?
It's not about chip number. I will show you. Just give me a second. Okay. So the idea of the JK flip-flop, if you see it, it's really, really crazy, which is using feedback control. So it's the same thing like S and R, but you know, I'm using what? I'm using feedback. How does feedback work? Let me show it to you. So basically, you know, our latch used to be like this, right? My nose. Anyway, so here and then there, and we have our lovely clock, and we have here S, and we have here R. Do you remember this? And then you know we have the like this, and then we have like that, and we used to call this Q complement. Correct?
Isn't this just SR flip-flop?
Yes, exactly. It is actually based on SR flip-flop, but you know, let's see what's the fun we're gonna do. So mathematician came into the conclusion that you know we have to feedback reverse the flip-flop to build something is called JK flip-flop. What does it mean? So they came into a way that you know remove S and R, and they call this J and K. Okay, so far nothing have been changed, right? The new changes is basically to come here with a new color and take in the Q complement and loop it back into the NAND of the J. And different color, which is this one, and you know, take the Q and you loop it back and you connect it to the, let me just clean this.
Sorry, Professor, is that a 3 input? Okay, got it.
Yeah. So this way, I built the first attempt of the JK flip-flop by what? Reverse the output feedback. So what I did, if you look to it, I added this and I added this one. Now I'm in JK flip-flop. Let's do the analysis to see whether this thing work or not, right? Because maybe you know I'm lying and I'm not telling you the truth. Who knows, right? So in that case, we need also the truth table. You guys agree?
Yes.
So if I do truth table here, if I do truth table here, it's gonna be what? It's gonna be the clock, and it's gonna be the J and K, Q, and Q complement. 1, 2, 3, 4. Because still, you know, we are using also the positive edge of the clock in this case, right? So let's make it like this. So it's actually reporting in positive. So the arrow is going up. So here's like up, up, up. Right? So I have here 0, 0, and 0, 1, and 1, 0, and 1, 1. So far, so good? Okay. Now, what was our problem? Our problem, it was 1, 1. You guys agree? Huh?
Yeah, it wasn't being used, right?
Yeah, exactly. So let's see how this will happen. So I'm a person who doesn't really like to memorize everything. So I'll just say X, Y, Z, 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. So here we're gonna be 1, 1, 1, 0, and this is our NAND. So far, so good. Now, if I'm in 0, 0, if I am in what? 0, 0, what will happen? I'm storing. Do you guys agree? I'm storing. If I'm in 0, 1, I'm gonna be still the same as before. I'm gonna be what? 1, 0, 0, 1. 1, 0, 0, 1. Now we're gonna check what will happen in 1, 1, which is really crazy. Okay, let's see. Now I have here 1 and I have here 1. Okay, so the tool said, you know, if I have 1, so basically I'm flipping. Do you agree? So I have here 1, I have here 1, and the clock also 1. So who will be flipping? The third one. So the third one here is Q complement is going where is going into this. So here I have Q complement, right? And here I have the Q. So far so good. So that means here I have Q and here I have Q complement, right? Are you guys following me? Or is not?
Yep.
Huh?
Yep.
Okay. So far we looks funny, right? You know, we are just getting Q and Q complement and we don't know what the heck, right? Now, this one is going into to be Q, right? And this one going to be Q complement, right? Do you agree?
Yes.
Which is representing Q in that case will be complement here. And here it's going to be Q. And if you flip one more time while still clock is high, that will be Q and that will be Q complement. And then that will return it back to be Q complement and then going to be Q. And then going to be Q complement and Q complement. So what we are doing here is actually what? Okay. So far so good.
For both, that would be Q complement
Huh?
for both. So for Q turns
No.
into
Of course, no. I understand what you're gonna be here, basically, what I'm saying.
Okay, that makes sense. Thank you.
And of course, they will keep flipping like crazy. And that's they call it toggling. Toggling. What is toggling? If I have a clock like this, this is my clock, right? Everybody can see my clock, right? Here is my positive edge of the clock. Here is my positive edge of the clock, right? That's clock. Then I have here the J is equal 1 and I have the K is equal 1, right? So my output here will be toggling. Q will be 1 and 0, 1 and 0, 1 and 0, 1 and 0, 1 and 0 like crazy. So how? I'm moving here into the positive edge of the clock. Since I am clock here positive and 1, this area there will be like this. And the interval between of them almost 0. And that's called oscillating. So the output here is oscillating or toggling. This is the problem. Because I'm going in something is called what? Not stable situation. So they fix the problem and they introduce a new problem. Do you guys agree? That makes sense?
Yeah.
How they fix this problem, they did something really crazy. Guess what they did? They built it in a bigger way. So they built 2 latches, one working in the positive, one working in the negative, and they overcome this problem. And in that case, officially, they considered the state wasn't used in SR to be a state flipping the state. So that means it's flipping Q. Okay, so fixing it is not really hard. Fixing it is a piece of cake. Fixing it is basically two latches connected to each other. Let me see how can I draw it to you. It's a little bit crazy. Let me see, because it looks really ugly, you know. How can I do it for you? You know what? I will do my best. Anyway, look, so gonna be here like an end, and here like an end. And then, you know, I have here like this, I have here like that. And then I have here the end. I have here the end. And I have here the clock in the middle, right? And I have here J and I have here K. Do you agree? That was basically our input. Then I'm not done. What I'm gonna do, I'm gonna also have here another latch. Okay, and then this latch is connected like this. Then we're gonna go like this. I'm gonna go like that. Okay, then somebody will tell me what is the next one. The next one, it will be taking the clock and flip it. Then I will do it like this. Then end of the day, this one will go here and this one will go there. By this way, I fixed the toggling situation, and instead of like that, what will happen? It will be flipping from clock positive edge to the clock positive edge. Again, what does it mean? It means that, did you see this isolation, right? Imagine my Q started here 1. Okay? So with this fixes in front of you, that one will go here from 1. I see the positive edge, I will be toggled. I will go here to be what? 1, up to the positive edge here. Then in that positive edge, I will flip. So I will be here what? 1, up to the new positive edge. Then I will be here low. So I stretch the interval of the clock, the oscillation here, to be what? Taking whole entire clock period between positive to positive. Does make sense? Hello? Hello?
Can you explain that one more time?
Again, definition of flip-flop. The definition, the traditional definition of flip-flop, 2 latches, each one running in the edge of the clock. That's actually the definition of flip-flop. But we never seen this in SR, right? But in JK, because the JK is the official flip-flop, is the one actually did that by generating 2 SR latch, helping each other to overcome the oscillation happening in the state wasn't used in SR. What exactly did, which is basically, I have here SR latch, do you agree? And this SR latch is reporting in the positive edge of the clock, while the negation of the clock will be responsible on the second latch, which is giving me the feedback produced with the JK to overcome the problem of the toggling in the state we used. How we gonna do, actually, how can we see this in the state diagram? What I'm actually doing in front of you is called state diagram. Did you see the oscillation here? Can you see the oscillation in this circle? Have you seen them? They're very close to each other like this, right? What I did, I stretched them. How I stretched them? Imagine my Q here is 1. Sounds good? My JK is 1, 1. And I'm now in front of the positive edge of the clock. So that means I went into the state which is flipping. You agree? So that means that one will be turned to be 0, but it's not going to be toggling anymore. What it will happen, it will wait to the second positive edge of the clock here, then it will flip. So that was 0, now it's turned to be 1. Then it will wait to another positive edge of the clock. Oh, I was 1, then I will flip to be 0. Then, other positive edges of the clock going to be 1 and so on. And that will be our official JK flip-flop. Does make any sense?
Mm-hmm.
Is it clear? Is it easy peasy lemon squeezy? Hello.
It's okay.
Why?
It's okay.
Look, this gentleman, show us that, there is a problem here, right? So instead of building a circuit which just like, one stage like this with feedback, we cascaded another latch, which is helping us to overcome this jumpy thing to be officially just toggling.
Mm-hmm.
And now that table, it's gonna be used to build the characteristic table. The characteristic table is really straightforward, right?
But
Because
the
I have
fix
you
is
what-
it still toggles, so your output is still Q naught instead of Q?
Exactly. So you're gonna be what? J, K, Q, and here Qn plus 1. 1, 2, 3, 4, 5, 6, 7, 8, and I have 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, and have here what 1, 2, 3, 4, 1, 2, 3, 4. Now, how are we gonna build this table is very straightforward. Any 0, 0 is a storing. So gonna be here 0 and 1. Any 0, 1 is gonna be as we see, right? 0, 1 is just like SR. It's gonna be 1 and 0. So gonna be here 1 and 0. Here we're gonna be 1 and 0. Then the 1, 1, 1, 1, it sees here Q, it will be flipping because it's toggling. So 0 gonna be 1, and it see here 1, it's gonna be here 1, it's gonna be 0. And I filled the characteristic table for the JK flip-flop, and I don't have any unused states in front of it. Any question? Is it clear?
Mm-hmm.
Easy peasy lemon squeezy. Do you agree? Come on, it's a piece of cake, right? From this table,
It'll take some time. It'll take some time.
yeah, you know, but you know, it shouldn't take too much time. Okay. Anyway, now we're gonna move into the the excitation table, right? So our excitation table, it's the same methodology we're gonna use for filling an excitation table by saying Qn plus 1 has JK and 1, 2, 3, 4 and 0, 1, 0, 1, 0, 0, 1, 1. And you know, from there we can see if 0, 0, we're gonna do the same story. Do you remember? So you know, I'm gonna get here a color as you can see and say 0, 0. So I have 0 and 0, and I have 0 and 0, and I don't have any other 0 and 0. So in that case, it's gonna be what? X1, X0, I'm sorry, right? So here it's gonna be X0. And then if I go in a 0, 1, I go here in a different color, which is basically like this, 0, 1. There is another 0, 1. Is there any another 0, 1? No. So in that case, it's gonna be here X and 1. So it's gonna be here X and 1. Then you know I have 1, 0. So I have here a different color, which is beginning 1, 0, right? Anybody can see any 1, 0 in front of him? So here is 1, 0. Here is 1, 0. In that case, I will have 1x. Then in 1, 1, that's not really hard. I just find a different color to make it easy. So I need 1, 1. So this is 1 and 1, and this is 1 and 1. So that's actually 0, and this is x. So gonna be 0x. And what I have in front of you is the excitation table of the JK flip-flop. Somebody will tell me, Professor, what about D and T flip-flop? If you can see them, you're gonna be laughing, literally. Guess what is actually D flip-flop and T flip-flop? It's just use cases from the JK flip-flop. Somebody can tell me how. I can show you and you would be seriously laughing. You know, if you already have a JK flip-flop like this, right? Here's the J and here's the K and here's the Q and here's the Q complement, right? And I have here the positive edge of the clock. If I would like to build a D flip-flop, so that means I'm gonna run out of the state of toggling and storing by flipping the relation. So what does it mean? It means that, you know, JK flip-flop is 0, 0, 0, 1, 1, 0, 1, 1, 1. Do you guys agree? 4 states, right?
Mm-hmm, mm-hmm.
If I go ahead and take J and I connect it to NOT gate and connect it to K, guess what? This is the D flip-flop. So what I did literally, I look into my table of JK and I take the state that is 1, 0, 0, 1. Do you guys agree?
Sorry, what's the D input? So this is the D flip-flop?
Yes. So, you know, I'm showing to you, it's a JK flip-flop, right? Look at the JK flip-flop. But
Yep.
you know what I did? I took,
You put a NAND gate.
I call it D, and I pass it to the J, and I take that wire and I invert it and pass it to the K. So what does it mean? If D is equal 0, so that means J is equal 0 and K is equal 1. If D is equal 1, that means J is equal 1 and K is equal 0. So those are the only 2 states I'm using from the JK flip-flop. Do you agree?
Yes, yeah, you don't have the 0, or 1, 1.
Exactly. Who gonna have them T flip-flop? Okay, so this is showing you D and T are the kids of the JK flip-flop.
I'm
So
guessing
it's-
T would
let's
be
do-
J and K connected, correct?
Yeah, exactly. Which is basically using 0, 0, and 1, 1.
Okay.
Storing or flipping. All right. That's why they call T, which is standing for transition, while D is standing for data flip-flop. Let's study them. I mean, it's not really hard. It's a piece of cake. So, you know, if I looked, excuse me, if I look to my table here, which is a JK and Q, I can make D flip-flop, right? So I can just go ahead and make here D flip-flop. And from the D flip-flop, 0, 1. And then I have here the QN. This is basically the truth table. So 0, 1, 0, 1, right? And I know that, you know, when is D is equal 0, D 0, 1. So 0, 1 from that table, do you guys remember what was called? 0, 1, so it was 1, right? 1, 0, it was 0, right? That's basically what we have. And you can just move forward to the characteristics and you will move to the rest of the whole entire problem. Let's look to the JK flip-flop when it's turned to be T. It's very straightforward. So, you know, if I go ahead like this and say, you know, T flip-flop with Q, so basically I'm talking about 0 and 1. So if T is equal 0, J is equal 0, and K is equal 0. If T is equal 1, J is equal 1, and K is equal 1, which is I'm talking about whether that I'm going to be storing or what. Huh? Storing and what? Storing or toggling. So is it a straightforward thing or not straightforward thing or what? If you have any questions, if nothing is not clear to you, I can fix.
What is the excitation state used for? Because I know characteristics for like the clock, like as
There is characteristic for anything in the world, right? There is
correct.
excitation also for this. Wait, why you said that? You know, now I'm disappointed. Look, you know, if you look to the D flip-flop, you already have DQ. Or, you know, QD, whatever you would like, you know, you do it, right? You know, here for instance, it's gonna be what? It's gonna be QN, D, and QN plus 1. 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. Right? This is the characteristic table for D flip-flop. What is the excitation table of the D flip-flop? It's gonna be like this: QN, QN plus 1, and D. 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1. Do you agree?
Yeah.
Same thing for T. But I'm gonna give it to you so you guys can look at it, because I would like to see whether that you guys understand what I'm saying or not. And next time I can even, you know, go ahead and cover it again. That makes sense? So today we focused on finishing all of the possible elements are used for the further implementation using sequential elements. So sequential circuits based on sequential elements, I'll do it. So sequential elements started by the SR attempt, which is SR latch, NAND base or NOR base. Then we figure out that, you know, it's handicapped, that, you know, there is unused states and also timing is not involved. Then we start involving the time by having clock, and we name this SR flip-flop, and we cover the characteristic and the excitation table, which followed by guidance from the truth table of the SR latch. Then we figure out that by feedback control that we can produce JK flip-flop, which is the early stage of it. It was having a problem, which of the state that had been resolved produced a new problem, which is not stable, and they call it toggling. This not completely toggling, it was actually completely in a big mess, going up and down in a crazy way, oscillating, they call it. Then they try to overcome the problem of oscillating by stretching the oscillation between the edges of the clock, and they call this toggling. Then they start trimming the JK flip-flop by putting negation of the K, while the J will be the not negated, and they call this the flip-flop. And then, they actually take the JK and they turn them with one wire. They call it T flip-flop, and that's actually used for the storing and toggling operation. Alejandro was asking for T, which is not really hard. So basically in the T flip-flop, I'm storing or not storing. Do you guys agree? So in the T flip-flop, if I have Q and D like that, right? So, D is 0, that means I'm JK is equal 0. So I'm storing. So that means Q is going to be as it is. But, D is 1. So that means, 1, that means JK are 1. And in that case, I'm what? Flipping the state. A state was 0, so it's going to be 1. In the reverse, 0, that means JK are 0. So that means, I'm QN is QN as a next going to be also 1. While in the last one, when D is 1, that means I'm JK is equal 1. So that means I'm actually toggling the current state. So the current state is 1, so it's going to be flip 0. So implementation of it is like XOR. Do you guys agree? Make sense? Then if I look here,
That was for T, not for D, right?
huh?
Just 'cause that table says
D,
D.
and then I will move to T. So make everything clear. If I look this to the excitation table, when I'm 0, 0, I'm 0 and 0, right? Is there any 0 and 0 again? Nope. 0 and 0, I'll put 0. Then, I'm 0, 1. So I'm 0, 1. There is nothing else, right? I'm 1. Then, I'm 1, 0, right? 1, 0, I'm 1. I'm 1, 1. When 1, 1 here, I'm 0. So I already filled the the excitation table of the T flip-flop. On the other hand, this is D or T, I forgot. This is T actually.
That was T, right? That's what I was asking.
You're right. I'm sorry about that.
$5.
That's T. That's T. So that's actually solved the problem for 100. Anyway, now we're gonna go into the D. What's the problem with D? D is basically data. That means, I'm using to push data. So basically, you need to learn about D is the element later on will be used for building registers, while T is the element used for building counters. So if I do it like this, and a clock, and I have D, and I have here the Q, so basically, every positive edge of the clock, D will equal Q. Sounds good? If you like to build a table for it, it's not really hard. So basically, I have here QN, D, and QN plus 1. 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1, right? And also the excitation QN plus 1, and D 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. Now we're gonna learn from the D is equal 0. D is equal what? Equal 0. So that means, J is equal 0 and K is equal 1, right? J is equal 0, K is equal 1. We need to see what does this mean? J is equal 0 and K is equal 1. I don't remember what was it. 0, 1, right? 0, 1. So gonna be 1. 1. Right? Now D is equal 1. So the flip 0. 1, 0, like that. I think there's something flipped here, but we need to do the D flip-flop again next time. It's not problem. Because I think when I made the loop, something had been flipped. Because normally it should be 0, 1, 0, 1. That means, the D, it should be equal the next. Do you understand what I'm saying? Hello?
Yeah.
Mm-hmm.
Make sense? Huh? Hello?
Yeah, I got confused at the end. Sorry.
Yeah. There was something that flipped here. Shouldn't be flipped like that. So that means maybe the table needs to be flipped again because of the.
So D should equal QN plus 1.
Exactly.
Mhm.
And then, normally this head should be 0, 1, 0, 1, and normally here that's gonna be 0, 1, 0, 1 also, because you are actually transiting data. Look, you're pushing data with the positive edge of the clock. But anyway, at least you understand the concept. That makes sense. So everybody now following what I said: SR, JK, and D flip-flop and T flip-flop. 3 things we are learning, huh? The characteristic table, excitation table, 2 of them coming from the truth table. Do you guys agree? Is there any question? T flip-flop is very clear. Okay, T flip-flop is very clear because using 0, 0 and 1, 1, so we don't have any problem. Maybe in the middle I flipped something, which can be a problem. It's not, some issues like 0, 1, 1, 0. This need to be 1, 0 here and 1 here, something like that. We can check here if you want. So if it's 0 and 1, right? So J is 0 and K is 1, right? Everybody can see what I'm doing, right? So I have here 1 and I have here 1 from the K, right? So I have here 0. In an AND gate, any input equals 0, what will happen? If any 0 happen in an AND gate,
It'd be 0, and then the output will be a 1.
Yes, but if the input is a 1, then we have to look to the flip. That was the problem. So yeah, based on this, they're gonna be here 0, and here we're gonna be 1. Here is 1, here is 0. Yes, now it works. Okay, look. Any question? Hello.
No.
There is no questions.
Nope.
Just redoing it right now.
Okay. Is it clear? Clear lecture? Something's not clear. If it's clear, write clear. If it's not clear, write not clear. Just 1 person said clear. My gosh. Just 5. The one who doesn't consider it clear, tell me why it's not clear. We need to do more. So why you don't revisit the recorded, and then if there's something is not clear, I can clear it up next time. What do you think? Okay, Luke. Thank you, I appreciate it. So it was my pleasure to talk to you. I hope that everybody will enjoy the rest of the day, and I will see you on Wednesday. We're gonna move forward with how can we change from one to the others with scientific steps to follow, and then we can after that start with introduction of finite state machine. Sounds good to everybody?
Professor,
Yes,
I
sir.
had a question about the test.
Which one?
Well, it's my question, like my 3A. So would I email it to you, or how do you?
What question?
It says you flip the problem. You take XS3 as input and get output as BCD.
Okay.
But my thing does get XS3 as input and output as BCD.
I will look at it. Okay.
Okay. Do you want me to email it to you, or how do you want me?
On the grid scope, I will look at it. Okay. Because your input XS3 and your output should be BCD.
Yes, that is what it does.
That's what you did, right?
Yes.
And that was in the truth table.
Yes.
Okay, I will look at it. Okay.
Okay.
Thank you. Have a good day, guys. Thank you. Bye-bye.
Bye.